Good evening.
Tonight, our speaker, Tom, is a keen amateur astronomer from
Joined Aylesbury Astronomical Society at the age of 9 and has been an active member ever since, before becoming chairman in 2018. He has an active interest in all aspects of astronomy, from looking through a telescope at the many brilliant objects in the sky to maintaining and the construction of telescopes mounts. And he also has an active interest in spaceflight and rocketry, delivering many talks on the subject, such as the space shuttle, comparisons of different launch systems and their pros and cons. He also has talks on guides to telescopes. So let's tonight welcome our speaker, Tom.
So my talk today is on the tyranny of the rocket equation. That is a title by an essay by NASA astronaut Don Petit, who was up on a STS-30 many years ago. And he wrote a three-page paper on how the rocket equation is tyrannical. So this talk is a summary of that, and hopefully it should be half an hour to 45 minutes on why it's such an awful equation to work with if you are into rocketry. So this is why is that not? There we go. So this is one of the quotes from his paper. Tyranny is a human trait that we sometimes project onto nature. This projection is a form of rationalization, perhaps a means to cope with matters that we cannot control. Such is the case when we invent machines to free us from the bounds of Earth, effecting our escape into space. If we want to expand into the solar system, this tyranny must somehow be deposed. So let us go on to work out why it is tyrannical. But first of all, we need to know, and I'm sure all of you do, we need to know what a rocket is. Now, this is a picture of Starship Flight 10, only a few months ago. However, it illustrates that a rocket is a momentum machine. That is all it is. We spew gas out of a nozzle at as high a speed as we can possibly imagine, with as much fuel as we can possibly get on the rocket, and the rocket then goes in the opposite direction. And I'm sure all of us have seen what happens if it doesn't, with many fantastic videos of launch anomalies. On that subject, there is a brilliant internet cartoonist called XKCD, and he many years ago produced this comic called Up Goer 5, and I appreciate that's a bit small. So I've zoomed in on the bit that we're interested in, which is the engines at the bottom. And it says, this end should point towards the ground if you want to go to space. If it starts pointing towards space, you are having a bad problem and you will not go to space today. So you would be acting your momentum in the opposite direction to where you want to go. So the rocket is going to turn around and you will not go to space. So with that little bit of flippancy over, let's actually get on to conservation of momentum, which is key to understanding rocketry in general, but also sort of main basic physics. So this is a law by Isaac Newton. Momentum is the product of mass times velocity. So if something's moving fast, doesn't weigh that much, it has the same momentum as something moving slow. If something's going fast, not much weight, is the same as something very heavy moving very slow. And I'm sure we've all seen demonstrations of pool balls and Newton's cradles and all of the other things where you get big objects hitting small objects, and then obviously the second one goes at a proportion to the first depending on the weight. But this only holds if no external forces act on the system. So the rocket equation only deals with momentum change. It does not deal with anything else. So all of the figures that you will see in this presentation are ideal figures. Of course, there is friction with the atmosphere. There's gravity losses due to when you launch a spacecraft, launch a rocket. It starts a gravity turn and has to try and stop gravity from pulling it back down. And that requires energy, which isn't in the rocket equation, but it does come into it. So we expel exhaust gas, as mentioned, at high speed out the back as fast as we can, and the rocket moves forward at a proportion of the speed depending on the difference between the exhaust mass and the rocket mass. And that is a very important principle that we have in this presentation, is the principle that although the rocket is going forward and is spewing gas out the back, it may not be quantifiable to say in this second it was this much gas, but we will have to quantify it at some point. So we in this talk are concerned with the rate of change or the rate of gas coming out the back in terms of mass. So I hope I've explained that okay. We're not concerned with the exact amount. We're just concerned with the rate at which it comes out. And of course, this was defined by Isaac Newton in 1687, and this was first applied to a rocket engine by the Russian school teacher, as it happens, Konstantin Tsiolkovsky in 1903. And he obviously defined the equation that we are looking at today. So it was first actually William Moore in 1810, a British mathematician, first came up with the idea that this could be applied to objects that move via momentum change. But he didn't actually, because of course rockets didn't really exist in 1810. The sort of field of rocketry was just about starting in 1903 when Konstantin Tsiolkovsky worked his equation. However, it wasn't really known about that he came up with it in 1903. Robert Goddard, the famous physicist and rocket engineer in 1912, independently derived the Tsiolkovsky Rocket Equation. And then that also wasn't well known in Germany. And Hermann Oberth, a German scientist, again, one of the fathers of modern rocketry, he also independently derived it about 1920, all based on work they saw from William Moore back in 1810. And then together, all three of them, they sort of laid the foundation for modern mathematics and spaceflight. Obviously, it's named after Tsiolkovsky because he is the person who first actually defined it without just coming up with the general concepts. So now we know a little bit about the history, a little bit about why it's needed and what a rocket is. Let's come on to the rocket equation. So this is it. This is what this entire talk is all about, which may look simple. It is delta V equals VE natural log of M naught over MF, which is equal to ISP G naught ln M naught over MF. So let's explain some of these terms. Delta V is the change in momentum. So that there is basically the currency. We'll come on to it later on, the currency for spaceflight. VE is the effective exhaust velocity. Again, we'll come on to that later. That's related in the second term to specific impulse and standard gravity. Those two are basically the effective exhaust velocity is the specific impulse times standard gravity. And then M naught is the initial total mass. So that's the wet mass of the rocket. That is the rocket, its fuel tanks, its plumbing, its fuel, its engines, everything that is on board when they say, and we have liftoff, everything on board at that exact moment is counted in M naught. And then MF is the final total mass without propellant, so the dry mass of the rocket. So again, that's engines, that's fuel tanks, plumbing, life support, everything there, except for the fuel. So I'm sure you can see in there, the fuel plays a big factor in how much delta V you have, but it also has that other term at the start. So now we've gone through what looks like a simple equation is. Let's have a look at each of these terms and work out which of these is the worst to deal with, which is the most tyrannical, and how they all come up and add up together to be a bit of a pain when you're trying to fly a rocket. So, but first of all, we need to know the first term. What are we trying to achieve? Well, we are trying to achieve delta V. So delta V is the change in velocity, the change in momentum, because when you're in space, of course, you do not change mass. I mean, apart from the fuel coming out the back, your spacecraft is the same weight for eternity. It's sort of the currency of space travel. Every time you need to do anything, you burn some of your currency. You burn some fuel, you spend some of your currency. If you need to do an inclination change in orbit, you will need some delta V. If you need to go into a higher orbit, lower orbit, deorbit, go to an escape velocity, whatever, you'll always need some delta V. So in general, delta V is the limiting factor for every single modern space mission. Even the satellites, the James Webb, I believe that's got enough fuel for delta V on board to be able to keep in one spot in space, to do that for about 10 years. And then that'll be it. We won't be able to control it anymore. We will have spent all our money on board and expended all of our delta V. And units for delta V are in meters per second, which relates to mass, but this specific term is in meters per second because, as I said, mass is constant. And we can do a bit of, if anyone fancies doing some maths later, during the derivations, we can work out exactly why it's meters per second and not meter kilogram per second. So why does delta V matter? So as mentioned, it is the currency in spaceflight. So here are two diagrams. And you can see they are maps of what you need delta V to get anywhere in the solar system. So on the bottom left there, that is Earth. And you can see if you follow the arrow upwards, which indicates a positive amount needed, away from the way the arrow is going, you will see that it requires 9.3 to 10,000 delta V just to get into Earth's orbit, which, I mean, it's pretty astonishing, because if you compare at all of the other numbers on that screen, which I hope you can see, yes, you need 3 times more if you wanted to deorbit from Earth all the way down to the sun's coronosphere. But to go to the moon, for example, you would need, say, 10 kilometers per second to get into orbit. You would then need 4.1 to get so that would be into low Earth orbit, into translunar, or to L4, it's 4.1, 0.72 lunar orbit, and then only 1.6 to land on the moon. So as Don Petit in his essay correctly states, that the giant leap that Neil Armstrong was referring to when he landed on the moon, this is one giant leap for mankind, wasn't him stepping out onto the moon's surface. It was getting into orbit in the first place, because that required 2/3 of the total budget that you needed in the first place. And you can see then on the other diagram, it shows from the planet's surface, all the numbers there going to the right show how much delta V you need to get into their orbits. And then the other numbers relate to how little or more delta V you need to transfer between each of these orbits. So you can see to get to Mercury for us would be getting out is 9.8 delta V, 9.8 kilometers delta V to get off the Earth's surface. Then only 672 into an elliptical orbit, and then only 69 into a heliocentric orbit to Venus, where we could be captured. So again, sending stuff to Venus, relatively easy once you're out the atmosphere. And then if you'll also note, Jupiter, if you were to land on Jupiter, which is a bit of a nebulous concept since it's a gas giant, but to get from a stable low orbit around Jupiter all the way up to an elliptical orbit takes 4,000 delta V. So if we had the same here, which of course we don't because we're a much smaller planet, then that would be quite the challenge just to get out of orbit once we're in orbit. But luckily we don't have that. So when you are designing any sort of spacecraft, you need to use this rocket equation to work out your delta V budget for every stage of your mission. Unless, which we'll come back to later, you can refuel. You need to go from launch, orbital insertion, transfers, landing, and any station keeping or course correction on the way. You have no chance to change that. So once you're off, you're off. Once it's in the air and the engines are lit, you are stuck with your delta V budget. So we've now mentioned delta V, but I mentioned a couple of slides ago engine exhaust or efficiency, which is the VE or ISP G0 term at the start before the natural log. Well, we need to work out what that term is now, because that is one of the terms that governs our delta V budget that we have. So let's move on to delta V. So we'll start though with effective exhaust velocity. So this is the average speed at which gas leaves the nozzle, and it is essentially equivalent to how much momentum is produced per unit of expelled mass. The higher you can get your effective exhaust velocity, the greater the efficiency of your engine, and the higher delta V for the same fuel mass, which I'm sure if you think about it, is fairly obvious. If you can go faster with the same stuff, it's going to be more efficient. Of course, we don't have things like speed limits in space. You can go as fast as you want. So the faster you can go, the better. However, effective exhaust velocity is not always equal to the actual gas speed. The effective velocity will change depending on the nozzle shape and if you are in a high pressure or low pressure environment. If you're in a high pressure environment and your nozzle is too big, your effective exhaust velocity will reduce because you will get effects where the flow detaches from the inside of the nozzle. And it's the same if you're in a low pressure environment and your nozzle is too small, then part of the exhaust will expand after the nozzle and therefore will not be counted in the effective exhaust velocity. I've just got to find where I am on here. Apologies. We are. So, specific impulse measures how efficiently the rocket uses the propellant if independent of Earth's gravity, which is why VE is equal to ISP G0, where ISP is the specific impulse. So it's a way of decoupling completely how much an engine can do without just referring it to Earth. Because of course, rocket engines don't just work on Earth, which we'll come back to on the next slide. And it is equal to the time 1 unit of propellant can produce thrust equal to its weight in a specific system. So if you've got a higher specific impulse, a higher ISP, your rocket is by definition the higher efficiency, because it can produce the same thrust for a longer time, or it can produce more thrust for the same time. So let's look at some specific impulses. And then the next slide is going to show you a graph of different specific impulses. You will notice at the bottom is the rocket. So let's come back to the rocket for a second. Obviously, if you are flying in Earth's atmosphere, you also have air exhaust coming out of an engine. When you're having a look at effective exhaust velocity, you only care about the propellant velocity coming out of the engine. And the propellant velocity, because of the force you're generating with the other air, the propellant velocity is going to be exceptionally high if you're also accelerating air with the fuel burn coming out the back. So at low speeds, air-breathing engines like turbofans, as you can see, the GE CF6 there, manages 6,000 seconds specific impulse at subsonic speeds, which, I mean, rocket engines we'll come on to can only dream of this. That's absolutely astonishing. The Rolls-Royce Olympus on the Concorde delivers about 3,000 seconds operating at Mach 2. And then the J58 turbine on the SR-71, that reaches about 2,000 seconds at Mach 3. So you can see here, the faster you go, the less efficient in general your engines, because combustion times are generally shorter. However, we'll come back to rockets now. Rockets are right at the bottom. They have a much lower specific impulse, typically a few hundred seconds, because they cannot accelerate the air that is also going into their engine intakes. They must carry both the fuel and their oxidizer on board. However, they cannot operate anywhere. The Space Shuttle main engine, the RS-25, achieves about 450 seconds, but that'll run all the way from ignition all the way into orbit, which obviously we can't do. And this is another thing we'll come back to later on, using air-breathing engines to try and get us a little way into space. So we've talked a little bit about general applications, specific impulse there. Let's talk about rocket engine applications specifically. So the RS-25 engines, as mentioned, the Space Shuttle main engines, they achieve an effective exhaust velocity of 4,400 kilometers per second when they operate in a vacuum. They are less efficient on the surface because of nozzle effects. The highest specific impulse we ever have achieved in a rocket engine was 542 seconds in a combustion engine with a tripropellant of lithium, fluorine, and hydrogen. And I'm sure those of you in the room who are anyway chemically inclined will probably understand that burning lithium, fluorine, and hydrogen and ejecting it out of a nozzle probably isn't the nicest idea. Fluorine ignites on contact with basically any fuel. Hydrogen is an explosive hazard, and lithium creates huge fires. And then to top it all off, what this puts out of the exhaust in vast quantities is hydrogen fluoride. So we do not want that around at all. And then just to boot, the exhaust coming out the end of the rocket is heavily ionized. So therefore you will be able to get no communication with the rocket either. So that's a complete non-starter. Something that isn't on this slide, which I feel I should mention thanks to our friends over in the East's recent cruise missile tests. The Americans also tried nuclear thermal rockets that differ from conventional rocket engines by the heat source is not combustion. The heat source is a nuclear reactor. In the 1960s, they managed to get liquid hydrogen gas, heating that up through a mobile flying nuclear reactor, which I'm sure everyone understands is very safe, and managed to get 850 seconds of specific impulse, about twice that of the space shuttle engines, at the cost of heavily radioactive exhaust. If we move slightly away from combustion engines and go to electrical engines, we have some examples here of electrical or light engines. And as you can see, the specific impulse figures here are brilliant. The Hall effect thruster on Smart 1, which is the DS4G, as on that slide, that will produce. Oh, hang on, sorry, I've got my slide wrong here. It'll produce about 20 kilometers. It's the top one, 20 kilometers per second of. Oh, sorry. It's 16.1 kilometers per second effective exhaust velocity, so it's very efficient, but a maximum thrust of 68 millinewtons. So obviously you can't use that in the atmosphere. Your drag will be too much, but in space, if you just want to push something for a very long period, you can get a great deal of delta V out of these engines. The variable specific impulse magnetoplasma rocket, the Vasimir engine, which is currently in development in NASA, would theoretically yield a maximum thrust of 5.7 newtons and approximately 120,000 meters per second of exhaust velocity for a 12,000 specific impulse, which is very impressive. The electrostatic ion thruster currently in development by the EU on DS4G. That is 210,000 meters per second exhaust velocity, 210 kilometers per second. So that again promises to be a very efficient engine, but again with low thrust. And then just to compare at the end there is a photonic rocket, which is the ideal scenario that has an effective exhaust velocity of the speed of light. So the specific impulse is absolutely insane, propelled by the photons emanating out the back of a torch. Essentially, when you turn a torch on, your hand is essentially undergoing photonic propulsion. But we are a long way from creating light bright enough to shine and be able to power us along. I mentioned during this slide the tripropellant of lithium, fluorine, and hydrogen. I'd just like to take a slight detour. If anyone is interested in learning about interesting rocket propellants, there's a great book. I have a copy here, which you might not be able to see because of my Zoom thing, called Ignition by John D. Clark. It's an informal history of liquid rocket propellants, and that has an entire chapter on specific impulse and rocket performance. And I'd highly recommend that you read this. It's not as dry as it sounds. I found it very interesting, but then that's not to say that other people won't find it interesting, of course. But I thought it was a very good book. So Ignition by John D. Clark. It's very highly recommended. So That is effective exhaust velocity and specific impulse related to how efficient your engine is. So let's look at the other term in the natural log is the mass fraction. So m0 over mf is the mass ratio. It captures how much of the rocket's starting mass is fuel versus how much of it is structure and payload. So as mentioned, m0 is the initial wet mass, including fuel. mf is the final mass, and the relationship is logarithmic. As you add more fuel, you get diminishing returns on delta V. So again, the mass fraction, if you just want it as a number, is defined as mp over m0, and it's related to the mass ratio by essentially the inverse of it. So if the mass fraction is 0.9, 90% of the rocket's total launch mass is fuel. Only 10% is structure and payload. A higher delta V, the higher mass ratio, gives a higher natural log function, and combined with a specific impulse gives a greater achievable delta V. But it also means if you have a higher mass fraction of fuel, you have less for rocket structure, less for engines, less for payload or anything useful on board. And this is one of the fundamental engineering trade-offs that rocket scientists have to make. So how mass fraction affects delta V? As I mentioned, it's logarithmic. So if you have 80% of your rocket is fuel, and an effective exhaust velocity of approximately 4,500 meters per second, approximately the space shuttle main engines, you can see that with 80% fuel, you can achieve 7,200 meters per second delta V. If you increase that to 0.9, so if you take away 10% of your structure or add 10% more fuel, but of course you will then need to carry that fuel, you will then need to contain that fuel and make sure you have it in the first place, you can achieve quite a considerable increase in delta V. And then even if you increase from 0.9 to 0.95, it's the same increase. The more fuel you can get on board, the higher you can go. So let's look at some typical mass fractions now. So the Saturn V, a multi-stage rocket, approximately 88% of that was fuel. And again, multi-stage rocket, we will come back to that later. That is a very important thing. But in general, as you can see here, 85 to 95% of their mass is propellant. You don't have any mass really spare for engines. You don't have much for tanks. You don't have much for payload. And this is why spaceflight is so expensive. For aircraft, approximately 40 to 50% is mass of their mass is fuel on takeoff because their engines are a lot more efficient. As we discussed earlier, they use air-breathing engines. And they have aerodynamic effects, which means they don't need to carry as much fuel. But still, taking off in a 200-ton plane with 200 tons of fuel on board, to me, is still quite a scary prospect. And then trains and cars, you can see for electric trains especially, that's 0.05 of it is fuel. And for a family car, assuming petrol, say, diesel one will be slightly less because they're in general heavier. 0.04 of it is fuel. And then just for a marvel of modern engineering, a Coke can, like I have here, and I'm enjoying throughout this talk, that's about 0.95%. 0.95 mass fraction stuff in it. So they are so light, they don't need much, and all the structure is provided in it by the Coke, much as rockets do. So this is another quote about mass fractions from Don Petit in his essay. A veteran astronaut who has been to the moon once told me, sitting on top of a rocket is like sitting on top of a Molotov cocktail. I took his comment to heart by first weighing a bottle of wine, emptying the bottle and weighing it again. Simple engineering allowed me to estimate and compensate for the density difference between wine and gasoline, with a rather humorous remark about the wine he was drinking at the time, and measured that a Molotov cocktail is 52% propellant. So sitting on top of a rocket is much more dangerous than sitting on one bottle of gasoline. And of course, a rocket, you're sitting on top of fuel and oxidizer. You're not just sitting on fuel. So let's have a look at some design implications of the mass fraction. The rocket must have engines, tanks, and plumbing. It needs a structure, a backbone to support all of that. It must survive the highly dynamic environment of launch. There's lots of fire. The rocket vibrates something terribly, and there's a lot of force. It must be able to fly in a vacuum of space as well as the atmosphere. You can't use wings, of course, in space, so you need rocket thrusters, which will add to your mass. Then there are people with their pinky flesh and their required life support machinery. Of course, you need to keep them alive. Life support equipment is notoriously problematic, complex, and heavy. If the cabin air gets a bit stale, you can't just open the window. You need all of the purification equipment for that. And then finally, if you want to return to Earth, and most crews do, although we'll see if the SpaceX Mars trips are one way, there has to be structures to protect the crew all the way down back to Earth. You can take wings with you, but they are incredibly heavy. Parachutes are light, and they give a big splash when you land. And the Soyuz, as Don Petit again in his essay aptly describes, the Soyuz goes thump, roll, 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 aptly described as a series of explosions followed by a car wreck. And then with all of this, you also want to bring some payload, which may just be human, but of course, sometimes you'll want some science to take up with you as well. So let's discuss why this is tyrannical. If the radius of our planet were a bit larger, there could be a point at which an Earth-escaping rocket could not be built due to the constraints of this equation. Let us assume that our rocket is built entirely like a Coke can. It is 4% structure, 96% propellant. It has no engines, nothing like that. Let us also choose base hydrogen oxygen, which is the most energetic chemical propellant we know that isn't that dangerous, and we're currently capable of using. And let's assume we can have the ideal scenario, which no engine will be able to get to. If we plug those numbers from earlier slides into the rocket equation, we can transform the calculated escape velocity into the planetary radius. That radius would be 9,680 kilometers. If our planet was 50% larger in diameter, even using ideal engineering, ideal rockets, ideal propellants, and getting no loss at all, no atmospheric effects, no gravitational effects, we would not be able to yet, with current technology, to venture into space. And that is the sole reason why this equation is tyrannical. So let's talk a little bit about how they came up with how we came up with this equation, the derivation of it. There are four major derivations of the rocket equation. We will go through two here quickly. We'll go through one based on acceleration and one based on impulse. There are two others. One is relativistic, and I cannot understand that at all. And the other one relies on understanding the integration of throwing rocks off the back of a boat, which is quite an amusing one, but we'll stick with these two in this presentation. So let's imagine a rocket at rest in space with no forces exerting on it. From the moment its engine is started, with the clock set to naught, the rocket expels gas mass at a constant mass flow rate and at an exhaust velocity relative to the rocket, which is the effective exhaust velocity. This creates a constant force for F equals ma, propelling the rocket that is equal to the mass flow rate times the effective exhaust velocity. Its total mass is decreasing steadily, though, because it is expelling the fuel as gas out of the nozzle. So according to Newton's second law of motion, its acceleration at any time is its propelling force divided by its current mass. Remember that force equals mass times acceleration, and that's where the mass comes from. The mass of fuel the rocket initially has on board is equal to m naught. For a constant mass flow rate, it is equal to m naught minus the structure of the rocket, so that's the mass fraction. For a constant mass flow rate, it'll therefore take a specific time to burn all of that fuel, which is related to the constant rate it is expelling it out the exhaust. So the equation on screen there just brings time into it. You can see F equals the same as the mass flow rate times the velocity, and at the bottom divided by the mass with a time element to it as well, because of course the mass is decreasing and it will decrease until it ends with the mass of fuel that we're burning. Let me just scroll down on here so I can get to here. So if we integrate both sides of that equation with respect to time from 0 to t, you will note that R is the change of mass at the change over time, which allows a substitution. You can see by doing that, we can bring a natural log equation for the integral to substitute the integral away. And then we can finally arrive at VE ln m0 over mf, which is indeed the Tsiolkovsky rocket equation as in its current form that we have discussed today. There is another derivation, which we'll go through incredibly quickly, the impulse derivation. All of these, by the way, I found very clearly explained on Wikipedia. So these equations, the last ones and these ones, I took my time to understand them and then copied them in, and I hopefully explained them okay here. So an impulse is thrust related to mass. That is an impulse, and it is also a unit used in spaceflight. We can represent the delta V equation at the top there as the integral of the change in mass over the time over the change in mass. Sorry, let me restart that. I do apologize. So T in this equation is the thrust of the rocket. M0 is the initial wet mass, and delta M is the initial mass minus the dry mass, so the mass fraction. So the integral of a force over time is the total impulse imparted to a rocket, assuming thrust is the only force involved, which we are assuming. Realizing that the impulse over the change in mass is equivalent to the force over the propellant flow rate, and the flow rate is equivalent to the exhaust velocity, we can then substitute the integral again for the natural log function and end up with the exhaust velocity with the natural log again of the mass fraction. So we can arrive at the Tsiolkovsky rocket equation by inspecting the impulse rather than the acceleration. And if anyone is confused by integration, unfortunately, because of the change in time and the change in mass over time in these equations, all the derivations include some form of integration. So I did warn on the description there may be some maths, but that's the hard maths over now. We can all sit back and relax without any integration. So how can we mitigate the effects of the rocket equation? I mentioned some of these earlier. We can refuel on orbit. Instead of carrying all the fuel from the start, we can add propellant later. Or we can use stuff that's already there. If we land on the moon, there's the possibility we can mine helium from the moon. If we land on Mars, we might be able to mine water from Mars, split that into hydrogen and oxygen, and refuel our rockets. We don't have to take that off the surface, so the wet mass and dry mass equation becomes completely irrelevant. Another way, of course, is we send fuel tanks into orbit, so we combine two rockets delta V into one. We can stage, which we'll come to in a second. If you stage a rocket, you reset the rocket equation favorably with the second stage because you are discarding empty mass on the first stage. Saturn V had 3 stages. You couldn't get the total delta V that Saturn V had with 1 stage. Even Falcon 9, which is the current most efficient rocket that humanity has built, the first stage separation there is required, even though it could go all the way into orbit. That boosts overall efficiency, and the main reason for that is that we can then reuse the main first stage. But we don't have to use rockets. I do have another separate talk on how one can get into orbit. You can avoid the full burden of your delta V changes by changing how you start off. You can launch in the air. You release your rocket from altitude already. You can save the first sort of 30 to 50,000 feet of ascent, launch it off a rocket, also gain a bit of horizontal ascent, and just go from there. You could use with new exotic materials, possibly space elevators, magnetic launch rails or mass drivers, possibly more use when there isn't an atmosphere. Or you could beam energy from the Earth if you were using powerful ion thrusters that are capable of overcoming Earth's gravity. You could beam energy to them instead of having to carry it all on board. Or, of course, you do the standard engineering solution. You reduce the structural and dry mass using carbon composites. You integrate your fuel tanks together using monocoque sort of designs for fuel and rockets. You reuse the components. You don't need for additional mass fairings or stages if you can reuse them between rockets and stages. And of course, miniaturization, as has been done so well over the last 30 years. So let's just quickly discuss in detail each of these. Both in situ resource utilization, which is ISRU, and on-orbit refueling tackle a core challenge. You do not, in those scenarios, have to carry all your fuel from launch. And that's the same, of course, if you refuel on orbit. Much like aerial refueling, Starship is hoping to demonstrate this in the next 2 to 3 years. Before heading off to Mars, it'll refuel in Earth orbit. Once it's on Mars, they are hoping to mine water ice or carbon dioxide from Martian soil to make liquid oxygen and methane, which is what the Starship engine is powered by, to refuel and then come back to Earth. The Perseverance rover currently on Mars has it's called a MOXIE experiment. That's a small-scale ISRU demo. It drills into the Martian soil, sees what's in there, and if we could possibly make fuel out of it. Both of these technologies could turn distant destinations into refueling stations. We could stay, go to Mars, put some tankers in orbit around Mars. And with current technology, these are the most likely ways to mitigate the tyranny of the rocket equation. Along with staging. So the key limitation, again, of a single-stage rocket, once early propellant is burned, you are still carrying tanks and engines. The rocket equation's logarithmic form means adding fuel gives diminishing returns. The mass will go faster with all your supporting hardware for the fuel. The mass will go faster than your delta V. By dropping stages, you remove useless mass that you're not using anymore, old fuel tanks, old engines, and you reset the equation. Each stage has its own smaller mass fraction, but together they add up to achieve high total delta V. Let's have a quick look at this. I did lie. There is a tiny bit more math here, but it's the rocket equation, which we are so used to by now. So for every stage, you can sum up the rocket equation of its individual stage. A one-stage rocket could have engines that are sort of okay at sea level, okay in a vacuum, and it might be able to achieve a single stage to orbit performance of 9 kilometers per second with a mass fraction of 0.9. A two-stage rocket with two mass fractions of 0.9, which admittedly leads to a much lower payload mass, but you can see that the increase in delta V there and the decrease in engineering requirement makes that all worthwhile. You can increase your delta V budget by well over half just by having two stages. And of course, in a two-stage rocket, another sort of primary advantage, the first stage will be good in the atmosphere, the second stage will be excellent in a vacuum. You don't need to mix the two. Let's have a quick look at alternative launch methods. Again, we are just trying not to take all of your propellant with you. If we wanted to use mass drivers on the moon or electromagnetic launchers, you accelerate payloads using linear motors, so using propellant that is essentially supplied by electricity on the ground. You're not taking that with you. So you don't have to take it with you. You avoid carrying it with you. You reduce your mass fraction issues. Another current development that's going on in California is spin launch, where they are going to launch a rocket by having a large centrifugal spinner, essentially. It'll go many thousands of RPM in the vacuum. They will release the rocket off the end of it, and it'll come out the top of a through a disc, a plastic disc, at many hundreds of miles an hour. And then again, you don't have to take all your propellant with you, but that's a bit of a weird one. You can use air-breathing engines or hybrid engines, so you don't have to carry as much oxidizer with you. So if you can carry some oxidizer with you for vacuum and just use the until you're, say, up to 100 kilometers, you can use the oxygen in the atmosphere. And local to me, down in Aylesbury at Westcott Venture Park, there is a company, Reaction Engines, who are attempting to build a Sabre engine, which should run on atmospheric oxygen at orbital speeds. And then the sort of the holy grail is the space elevator. Of course, with that, you don't need any fuel. You could just winch your way all the way up into orbit. But that is that's a bit of a pipe dream with current technology. Let's have a quick look at a beam-powered propulsion. If you so instead of having a nuclear reactor, say, heat up or combustion, heat up all the propellant to spew out the back of your rocket at high speed. If you beam a bunch of energy up there and heat up, say, liquid hydrogen to vast temperatures and then pump that out the nozzle, you could get quite decent specific impulses without having to have as much propellant on board, because you can increase the effective exhaust velocity. Something else that has been investigated is you can use light sails. We either have powerful lasers on Earth or in orbit to fire at a sail on a spacecraft. That'll impart reaction from the photons hitting a reflective surface and propel it forwards. We have done this with solar wind as it stands. Of course, that's not light itself. That's more more particles, but it shows it is possible. And that would allow long duration, low thrust propulsion, ideal for interplanetary missions. And this completely cheats. This increases your delta V budget massively, because you do not need, apart from station keeping or course changes, you don't need to do anything at all. You just put your sail out and off you go. But as mentioned in the cons there, of course, that requires an awful lot of infrastructure, or in the case of a sail, you need to take that up into space. So you need to work out how to get that unfolded in space in a way that's going to be nice and it won't be sort of affected by micrometeoroids and be stable long term. And here, I've just got a little diagram here of a rocket. So you can see there, combustion gas heating and blasting gas out the back. Beam propulsion, you send a laser up, you target your spacecraft, which is obviously futuristic. And then space elevator, you just winch it all the way up. And then let's have a quick look at the Oberth effect. As we heard earlier, that Oberth also developed the Tsiolkovsky Rocket Equation. This isn't really a mitigation, but it can improve your delta V budget if you do it properly. So a rocket engine always provides the same delta V, but the energy gained from that thrust will depend on the existing velocity of the rocket. So in this presentation, we've mostly been thinking that the frame of reference, t = 0, and the velocity is static. However, that's not always the case. If you're in orbit already, heading towards a planet, you are accelerating down into that planet's gravity well. Kinetic energy depends on the square of the velocity. So the same burn at a high speed yields a much larger increase in your kinetic energy. In orbital terms, that means burns are much more efficient when the spacecraft is near periapsis, when you are moving fastest in your orbit, either in Earth's orbit or in another planet's orbit. You can add energy to your spacecraft more efficiently and get a higher total delta V for the same fuel mass, as long as you are going into a gravity well. So it's a little way of cheating the equation, and you see this all the time. If we want to go to, or Voyager 1 and 2 did it, and I think New Horizons that went to Pluto. New Horizons specifically went from Earth. It had a gravity slingshot using the Oberth effect at Venus, Mercury, Venus, Earth, Venus, and then started out on its long journey towards Pluto. So we'll come now to the conclusion of the talk, which again is another quote from Don Petit. The giant leap for mankind is not the first step on the moon, but attaining Earth's orbit. If we want to break the tyranny of the rocket equation, new paradigms of operating and new technology will be needed. If we keep to our basic rockets, they must become routine, safe, as affordable as airplanes, which is a viewpoint that Elon Musk has certainly proposed with his SpaceX rockets. And he also mentioned in situ resource utilization. But at the end there, the discovery of some new physical principle could break the tyranny and allow Earth escape outside the governance of this rocket paradigm. It could be that the rocket equation as it exists now, it could be that there is a way of completely cheating it, which we don't have to keep to our engineering. We can build a completely different thing, a space elevator, for example, and therefore we can completely ignore the rocket equation, at least for getting out of Earth's orbit. So I hope I've sort of been able to give you an insight into how it's tyrannical, how if the Earth was only 50% larger in radius, we wouldn't be able to achieve orbit with our current technology. And if anyone has any questions, I hope I haven't sort of bamboozled everyone too much. Then I'll try and answer any questions.
Tom, thank you very much. I don't think we've lost anybody online, and I haven't heard anybody creep out of the room. So we're ahead of the game. As usual, ladies and gentlemen, if you are online and you want to ask a question, put a digital hand up. Henry, I've already seen your hand in the room. Attract my attention, and Roy will bring over a microphone so that everybody can hear you. While you're thinking up your questions, Tom, one of the things that struck me was your quote about your statement about the size of the Earth. If we were 50% bigger, we wouldn't be able to get off the planet using rocketry. The thought I had was that in that case, if you were looking for civilized or looking for a space-going civilization outside our solar system, you shouldn't be looking at really large planets. Does that make sense?
That's an interesting thought, but it could be that they have a different technology. It could be they have managed space elevator. It could be they've managed mass drivers. If their atmosphere is different, they might be able to use air-breathing engines to get further up. So I don't think, I say the equation limit is just for us with current technology that we currently have. So I think that's an interesting thought. But
there's mitigation there.
Yeah, I think with sort of especially with the air breathing, because obviously because we can get into orbit, we're using traditional rockets. We haven't had to investigate air breathing or any other mitigations because we know we can do it. And although there are companies now working on ways to try and mitigate it a bit further, there are other companies just pushing ahead and going, okay, well, we know how to do this. We'll just improve the current rockets that we have.
I'll come back to the Sabre engine in a moment. But online, we've got Henry. Henry, can we have your question, please?
Right. Looking at two extremes, the moon landing, they were on top of a Saturn V-B rocket going to the moon. They couldn't have climbed up that on a ladder. They landed on the moon, and they were able to climb up to above their rocket on a step ladder. So there was very little. There was very small amount of power to take them off the moon back up to the circuit, to Collins on the outer. The other extreme is if you were on Jupiter, one of Jupiter's moons, and you wanted to take a sample and return to Earth, that would be probably impossible without the Saturn V rocket out there.
I think so. The Jupiter's moons are still a lot. I mean, they're slightly. I believe that they are approximately moon-sized. We know we can get a rocket down, but at the moment we are struggling to work out how to get a rocket back up. So Perseverance has got a whole bunch of samples that it's gone and capped up on Mars, and it has dumped them. So on Mars, Perseverance rover has left a little trail of metal things going along with samples. And as you say, we are going to need an enormous rocket to get them back. So we've got the samples there, and no one's quite worked out how we're going to get them back. So that is currently, you are right. We will need something capable of going from surface to orbit on one of those bodies, either a Jupiter moon, is that how you say it? Or Mars. And yeah, we're still trying to work out how we can do that.
Yeah, the Jupiter moons have the problem that they are within the gravitational attraction of Jupiter.
So that isn't, if we can work out on-orbit refueling, that isn't a massive problem, because we could just stick a tanker above the moon. We come up into orbit, we could then refuel and then come back. And that's, I know that's one way that they're thinking of doing the one for Mars, sitting a tanker in orbit there with a starship, taking off from Mars, refueling in orbit, and then coming home.
Good.
Okay, Henry. Tony Morris in the room.
Hi there. Just looking at the equation on the screen, I seem to remember a quote from some of the Apollo engineers that delta V was actually limited by the fact that you didn't want to turn your occupants into a jelly. So there's actually a limit on delta V. And just as an illustration against that, we see military rockets. They've got tremendous delta Vs, but yet they've not got a very high amount of fuel.
Yeah, so I think there's a slight confusion between G and delta V here. So delta V in this context does mean the change in velocity, but it's change in velocity irrespective of time that change in velocity happens. So obviously a military, I mean, I know the Russian Indian BrahMos rocket goes from I think it's Mach 1 to Mach 10 in approximately 8 seconds. That obviously a human couldn't survive that. But it still has the same delta V as if it did that over 80 seconds, just at a slower acceleration. So it's the acceleration for humans, the pink squishy things that we need to keep alive. It's acceleration for that in terms of G rather than the total change in velocity. Because when you go into orbit, I mean, orbital speed is 25,000 meters per second, but that happens over tens of minutes, the acceleration required to get up there. So it's not the instantaneous force, it's the instantaneous force applied to a human that will cause problems, but not the total change in velocity.
I'm not convinced of that, because that wasn't the original Apollo engineers' arguments.
Right. I'm sure that Tony's going to ponder on that for a few moments. We'll have to come back to him. Before we go on, Tom, could I just ask you to stop sharing your screen?
Yeah.
So we can see all the usual suspects. I'm looking around for questions in the room. Graham.
The concept of the space elevator, which I assume is meant to be taken literally, do I take it that the top end of the space elevator is something in low orbit, and therefore the whole structure must be moving quite fast with relation to the ground?
As far as I understand, the concept of the space elevator would mean that it has to be 25,500 kilometers up at geostationary orbit, because otherwise you don't want the end of the space elevator whipping around on Earth once every 90 minutes. So
I thought it would take a very long railway to do a orbit around the Earth at that speed. Yes, so it's geostationary.
So that's all the science fiction and everything. Well, I say all of it, apart from one that I know of. All of them refer to something being in geostationary orbit.
So it comes down to the strength of your wire, basically. Yes.
Yeah, exactly. Yeah.
Fine.
will the counterweight have to be in geostationary orbit rather than the actual terminus of the elevator?
So the terminus of the elevator would be at geostationary, and then there would be counterweights beyond that because you have to keep tension on the wire. So you've not only got the orbital mechanics of the wire being pulled, you've also then got to add counterweights on the other end to keep it taut, increasing the strength required in the wire. So yeah,
But that means that the counterweight would be whipping around, because anything over geostationary would be moving slower than the Earth's rotation. It would be dragging.
I haven't really looked into this in detail,
Right,
to
okay.
be honest. As far like if you had a space elevator, you could then pipe propellant up to it to be able to do things that maybe you wouldn't need a counterweight for.
Right, okay. We'll leave that some deep thought, I think. Roy Gunson.
Just coming on to the space elevator. I mean, it's a bit of advertising. We've got a speaker coming on 15th of January from United States, Larry Bartosek, who is part of a consortium who are looking at designing space elevators, primarily for things like Phobos and Deimos, my understanding is. So if you're interested in space elevators, don't forget our talk in January.
15th of January. Segways now. Look at that. We're getting posh. Tony, do we want to go back to you? So he's had a think, and it's Tony Morris again.
And I've left that one alone. I was thinking about your table. You were showing the different energies from a rocket to a coke can. And on there, you're on an electric train.
Yeah.
So the electric train has got an external energy force. So I don't think it should be on that table.
It's a cheat.
That is a fair point. So with that, I'm mainly referring to the energy of things like the pantograph, the wires, the traction motors, all that kind of stuff, the things that are needed to be able to use the electricity. But I do agree that having that on there is a slight cheat.
Okay. Going back to reaction engines, I read that unfortunately they had to fold earlier this year, and that basically they're in administration, but the intellectual rights have been bought up by another syndicate. Is that your understanding?
I hadn't heard about that. That's a real shame because, as I said, they are based very close to Aylesbury, or they were. And I know they got an engine pre-cooler prototype working, which could, I believe, liquefy air at Mach 2. So that's 100 or so degrees down to minus 149 in approximately 0.2 seconds, which was a very impressive feat. So it's a real shame if they have had to sadly stop development.
I think everybody's been in it. Well, everybody, interested parties have been scrabbling for intellectual copyright on the details. And of course, the American defense people had a big stake in it as well. So goodness knows where the intellectual copyright has gone there.
Yeah.
So
I mean, that is the holy grail, a single stage to orbit aerodynamic vehicle. That is powered by air breathing engines and then rocket engines further up. That is the absolute holy grail of modern tech for space flight. So if we can get there, that would be amazing.
Right. I'm looking for questions. Thank you to Mike Scollin, who's put up some details on the chat for those people who can't see it. Fountains of Paradise by Arthur C. Clarke describes construction of a space elevator. And he goes on to say, Clarke said that construction would go through 3 phases. It's completely impossible. It's possible, but it's not worth doing. I said it was a good idea all along. Okay, so I think we're definitely in phase 1 at the moment, and up to our knees in it. I'm looking around for any other questions. I'm not seeing anything in the room. I'm not seeing anything online either. So, ladies and gentlemen, will you join me in giving Tom Gillespy a big Bexman Swinton Astronomical Society? Thank you. Thank you very much, Tom.
Well, thanks very much.